Starting off with acids and bases, we're going to do a little concept check here. Looking at three generic weak acids, we have HA, HB, and HC. The image shown here represent the ionization of each acid at room temperature. So which acid has the largest Ka? Now remember, when we're talking equilibrium constants, the larger the Ka, because you remember, or K, remember, is products over reactants. And if we're talking about acids, we're talking about acids, splitting apart into their ions, which one of them, of course, is hydrogen. The other one will be the anion. So the largest Ka is going to have more of the products, which would be the ions on the top, and less of the reactants here, which would be the acids staying together, bonded together. So take a moment to think about that and look at the different diagrams and decide on which one will have the largest Ka. Hopefully you paused for just a second to look at your diagrams. If you look here at diagram HA, it shows pretty much only one of the acid molecules has actually broken apart. We're looking here at this one, we see many of them have broken apart and so forth, as you can see in our lovely diagram here. And then if we look at H, so that was HB, HC, we have 1, 2, 3, 4. So only two molecules, this was two molecules, have broken apart. Here it looks like 1, 2, 3, 4. So this is 4 molecules that have broken apart. And then here, this was just one molecule that had broken apart. So obviously, the one that did the most ionizing, or forming the hydrogen and its conjugate over here, was picture B, because it ended up breaking apart 4 of the molecules into the ions of the H plus and the B minus. So this one would have the largest Ka value, the largest Ka, because it's the one that made more of the products rather than the other two, which left most of them as reactants. And there is our answer. All right, strengths of acids. Some things to consider, strengths of bases too. Acid strength depends on the degree of attraction of the acid, anion, and the H plus. So how strongly attracted to it the anion is the H attracted to. If it's not a very strong attraction, it's going to more easily break apart and ionize. So if it's less strength, that means that the acid would be stronger because it's more willing to detach the H. If it was weaker, that means it has a stronger attraction for its hydrogen, so it's less likely to let it detach and become, an ion in water. Common acid-base strength is measured by the equilibrium constants or the ionization constant. Like I said, they like to use this word ionization here. So as you can see, you have the reaction in general is the acid plus water gives you the conjugate base, and hydronium, which is the conjugate acid, or the base plus water gives you the conjugate acid, and then hydroxide is the conjugate base. So I don't think this is supposed to be here, but anyways. So the base plus water gives you the conjugate acid, and then hydroxide, the conjugate base. Smaller the ionization constant, the weaker the acid or base. So as you get, times 10 to the minus 7 or 10 to the minus 9, as it keeps getting smaller, the weaker it's going to be. The position of equilibrium depends on the strength of attraction between the anion and the H. So in comparison, as what we said about the acid, the stronger the attraction means a stronger base or a weaker acid. So a stronger base is going to hold on to the H plus. A weaker acid will also hang on to the H plus. Now that seems a little bit backwards, but the stronger base right, will attract and accept that hydrogen ion. The weaker acid's going to hold on to that stronger, or hold on to that H plus. So here showing a diagram, the weak attraction. If it's not holding on to it very well, it's going to do the ionization, complete ionization. Where if it has a strong attraction, it's only going to let go a little bit of it, so it's going to only let a very small fraction of the particles actually ionize into H plus and A minus, which would be the anion. Now looking here, Ka, the acid ionization constant, or the equilibrium constant, whichever way you want to think about it. And you're usually going to see them for weak acids. Not going to see Kas for like HCl or any of the other strong acids. It establishes the amount of acid that ionizes in solution. It's a quantitative measure of the strength of an acid in solution. So like I said, larger Kas are going to ionize more, smaller Kas are going to ionize less. Now, we write out the reactions the same as before. The acid plus water gives you hydronium, and the conjugate base over here. And if you're writing it the Arrhenius fashion, the acid just breaks apart into hydrogen and the conjugate, or the anion here. So you can write the equilibrium expression using either of the equations. What you'll notice here is, it's still always products over the reactants raised to the power of the coefficient, just like before. And what we notice here, that these are usually 1-to-1-to-1 type molar relationships. But if you're using the top equation here, which is the Bronsted-Lowry type version of the acid, where you're donating to the water, we're not going to include water because it's a liquid. So the liquid gets omitted from the expression. You still put product 1 times the concentration of product 2 over the concentration of the original acid on the bottom, like so. And then if you're using the more Arrhenius version here, still you have your product 1, product 2, and your original acid that goes on the bottom. They're all AQ. And remember, anything that's AQ gets included into the equilibrium expression. You would omit only liquids and solids here, and the only thing you're really ever going to see present in acids and bases is it being in water, which would be a liquid. So we would never include water into the equilibrium expression. So this table is very nice. It kind of sums everything up. Strong acid, the Ka is large. We don't even really assign Kas to them because they pretty much go to completion. Ka is small for the weak acids. The equilibrium position far to the right for our strong acids because it pretty much goes to completion, and far to the left because, like I said, very, very small percentage of them actually ionize. Equilibrium concentration of H plus compared with the original concentration of the acid. Because we know this one completely dissociates, about almost 100% dissociates or ionizes. That means whatever you started with in your original acid is equivalent to how much hydrogen gets ionized or changes over into hydronium as well, because that H plus typically attaches to a water. So that's pretty much equal. Now, if we're talking weak acid, you get very little of the hydrogen or hydronium, and you have a lot more of that original acid still floating around because it has that stronger attraction for the H, so it stays attached to it. Strength of the conjugate base. For a strong acid, the conjugate is much weaker base than water. We call these ones neutral conjugates because they don't react with water, so they are much weaker base than water. They just float around in between, don't react with water. The conjugate base of the weak acid is much stronger base than water, so it does actually react with water. You'll see some instances of this later on where it reacts with water. We call them basic anions because they pull off an H and then produce some hydroxide in that particular situation, but we'll cover that later. Here's a nice table of a bunch of different Ka values from chlorous, nitrous, hydrofluoric, formic. So we're getting into some of the organic ones here, as you see, formic, benzoic, acetic. Okay, those ones, the phenol here is acting as an acid. So some of these ones are organic, as you can see, and really you're just looking at that front H as being the acidic H. The other H's in the rest of the formula are not part of this, being the acidic H's. But as you can see, the weakest ones on here are going to be down here with the 10 to the minus 10. Their pKa's are pretty high. Remember, pKa is just the negative log, so it'd be like the negative log of the Ka. It's going to give you your pKa, which is just a measure value if you want to look at it in whole numbers versus the scientific notation idea here. But large pKa's obviously mean very weak acids. The lower pKa's are going to be stronger, and then you have a larger Ka value. So up here, chlorous acid being 10 to the minus 2, that one would be the strongest on this chart. This is the strongest for this chart, and then of course down here, the lowest amount is going to be the phenol, which is going to be the weakest on this chart in terms of the Ka values. Base ionization constant or equilibrium constant for the base, also usually on the weak side here. We don't really assign KBs for like sodium hydroxide or potassium hydroxide, those really strong bases. Establishes the amount that ionizes in solution, and it is a quantitative measure of the base strength. So here you have your base plus water. This is following the Bronsted-Lowry example, giving you hydroxide and the conjugate acid over here. This is your conjugate base, this is your conjugate acid, but this is the basic reaction. And as before, as we looked at with the Ka, it's still going to be products over reactants. We will not include liquid water into the expression down here. So we have our first product here, concentration, times the second product, concentration, over the original base on the bottom right here. And these are all going to be designated as AQ, dissolved in the water. So they all will be written into the KB expression or the equilibrium constant expression for weak bases here. One thing to note about Ka and Kb, when the acid and base are in conjugate pairs, like you have, say, you know, the HCN and CN. So here's our acid, here's our conjugate base. Each one's going to have, this one's going to have a Ka, this one will have a Kb value. But since they are opposite in terms of, this is a very weak acid, this is a stronger conjugate base. You'll see their numbers later, but that the Ka times the Kb is going to equal the Kw. And of course, this is measured at 25 degrees Celsius because we're using the Kw as 1 times 10 to the minus 14. So unless otherwise stated in the problem that the temperature is not at 25 degrees Celsius, you can automatically assume that it is. But Kw will equal the Ka times the Kb for these type of questions, and it's a very helpful, useful tool because sometimes they give you the Ka for the acid, but you really need to know information about the base, and so you can find the Kb for the conjugate base there in the problem. Quick review of examples of conjugate acids-base pairs and how to work them. Remember Bronsted-Lowry definition, you have your H donors and you have your H acceptors over here. So when we're working with that, that creates these conjugate acid-base pairs. So for going from the base over here to the acid, we need to add in an H+. Adding in an H+, of course, is going to make this NH4. So adding the H, but then this one has a charge of +1. So you're adding in an extra with a +1. So that, of course, gives us ammonium for the acid in comparison to the ammonia base. Now, if I'm going the other direction, I'm going to take away my H+. So I'm removing the H, getting F. But because I'm removing the plus as well, that makes this a -1. So which direction you're going, add the H. So here, adding the H+, that's going to make this H2S. And then here, of course, this is where you would subtract the H+. And in that case, taking away the H is going to make this S -2, and so forth. This is going to be HCO3 with a -1. Removing one of the H's, and then of course if we added an H to this guy over here, this is going to be HCO3 -1, which is bicarbonate, or what you would call hydrogen carbonate. And as you can see, the hydrogen carbonate is just like water. It happens to be amphoteric, so that it can donate an H and it can also accept an H. This substance, the bicarbonate, it's called bicarbonate, or hydrogen carbonate, is one of the main components in our blood buffer system. So we'll be talking about that in a little bit more detail, but it acts as a good way of being able to take on extra acid in our system. Okay, so there you have those. Also wanted to point out, every anion can be thought of as a conjugate base of an acid, because you take away that H, it becomes the conjugate base. So there, technically, every anion can act as a base. The stronger the acid, the weaker the conjugate base, though. Remember, they work in that kind of tandem. If you have a stronger acid, you have a weaker conjugate base. If you have a weaker acid, then your conjugate base is stronger. So as you can see here on our chart, our strong acids over here, if you look at their conjugates, typically when they say neutral here, that's going to be pretty much has no strength as the base. The weak strength, base strength, and this will have Ka values. These ones will have Kb values. Now, the Ka value is a little bit stronger. That means the Kb value is going to be a little bit smaller and weaker. If the Kb value is the larger value, then that means the Ka value is going to be the smaller or weaker side. And then here, looking at the strong bases, okay, and then negligible, also putting in that neutral category of not being very strong. All right, so let's look at an exercise here. Let's take a look here. We need to calculate the Kb values for acetate and cyanide, who happen to be the anions of these two acids. This is acetic acid and hydrocyanic acid. So it's very simple, easy to calculate the Kb values because we have that formula, Kw equals Ka times Kb. And that means it's going to be 1 times 10 to the minus 14 equals the Ka in this case for the acetic acid. You know, that would be times the Kb, and you can easily isolate the Kb. Kb is going to be equal to the 1 times 10 to the minus 14 divided by the 1.8 times 10 to the minus 5. And this ends up giving us a 5.6 times 10 to the minus 10 Kb. Like so, this would be the one for the acetate, C2H3O2. Right there. Now, if we're looking at the cyanide of the hydrocyanic acid, so cyanide I'll do down here, that's going to be the 1 times 10 to the minus 14 equals the Ka in this case. The Ka is 6.2 times 10 to the minus 10 times the Kb here. And what we will see here, times 10 to the minus 14 divided by 6.2 times 10 to the minus 10. This one ends up being a Kb equals 1.6 times 10 to the minus 5. Now looking at these different values for the cyanide and for the acetate here, what you should notice is the Ka for the acetate is 10 to the minus 5. So this is a stronger acid in comparison to this one, where it's 10 to the minus 10. But what you should also see here is that makes the acetate the weaker of the two conjugate bases. So this conjugate base is weaker, whereas the cyanide, which is 1.6 times 10 to the minus 5, this one's going to be stronger in terms of the two conjugate bases, if we're just comparing those two directly, like so. And our answers do match, which is good. All right, another concept check. Speaking of, if the equilibrium lies to the right, the value of the Ka is. If the equilibrium lies to the left, the value of the Ka is blank. So take a moment, maybe pause, see what you can fill in for those blanks. Pause the video for a second, and then come back here and turn it back on to go over the answers. So remember, if the equilibrium is to the right over here, K of course is products over reactants. That of course makes the numerator the larger number. So the Ka of course is going to be greater than 1 in terms of that proportion of the products over the reactants. And in our case, our products are the ions, the hydronium, and the conjugate over the reactant in this case would be the weak acid. So if it lies to the left, of course, that opposite is true. So here, in that case, the reactant number is going to be higher, that original acid. So the Ka is going to be less than 1, following the same equilibrium principles that we once learned back in Unit 7. Same thing applies here for the acids and bases. All right, looking up here at this generic HA acid, weak acid plus water gives you hydronium and the conjugate over here. If water is a better base than the conjugate base over here, or conjugate base, do products or reactants dominate at equilibrium? This is another good conceptual idea. So when we say better base, we're talking about being better at accepting and attracting that hydrogen ion, that H plus ion, that proton. So if water is better at attracting the H plus than the A minus over here, this conjugate base, think it about for a second, maybe pause, decide, are we going to have products or reactants dominate? So definitely, if water's acting as a better base and attracting the H pluses to it, that means it's going to go this direction. So yes, the products are going to be the ones that dominate at equilibrium. Now, the opposite is true. If this conjugate base was a better base than the water, it would go the other direction and reactants would dominate at equilibrium. So does this mean HA is a strong or weak acid? We'll recall those conjugate acid-base pairs then. We said water is the better base or the stronger base in terms of that ability to attract the H plus here. That means this one's the weaker base. So if we have a weaker conjugate base, the weaker conjugate base means the original acid must have been stronger. Say they kind of go in tandem. The stronger acid yields a weaker conjugate base. a weaker acid yields a stronger conjugate base. So we would say HA then would be strong in this particular case, because we know that the A minus is a weak conjugate base because it can't even, beat out water's attraction for the H plus ion. All right, is the value of Ka greater or less than 1? Well, we know this is a strong acid, and water is the better base, or the stronger base out of the two. That means it's going to push the equilibrium towards the right. So, according to Ka here, products over reactants, then we're pushing to the right. That means that numerator number is going to be bigger. So Ka is going to be greater than 1. Greater than 1, because the strong acid pushes it to the right. All right, this is a nice fun one. So we're going to first look at the numbers and compare the numbers and then actually do the calculation. Discuss the value of K for the reaction. We have hydrocyanic plus fluoride gives us cyanide and hydrofluoric acid, all aqueous here. And is K greater than 1, less than 1, or equal to 1? Ka for hydrocyanic, 6.2 times 10 to the minus 10, and hydrofluoric, 7.2 times 10 to the minus 4. So the first question you should ask yourself is, which is the better acid? Which is the stronger acid? And by looking at the numbers, hydrofluoric is definitely stronger out of the two because it has a larger Ka value. So if hydrofluoric is the stronger one, it's going to more readily ionize its H+. So the equilibrium position would shift this way, because the hydrocyanic is a weaker acid due to that 10 to the minus 10 value. This is a much smaller Ka, value, and therefore the equilibrium position, if it pushes left towards the reactants, that means the K is going to be less than 1. That definitely also makes sense too if you think about the conjugates, because hydrocyanic produces this conjugate base and hydrofluoric produces this conjugate base, if you're looking at it from either direction. But if 6.2 times 10 minus 10 is for the acid, that means this conjugate base is going to be much stronger. And the hydrofluoric, the fluoride from the hydrofluoric is going to be, this one's going to be the weaker conjugate base. And out of the two, this one would be the stronger conjugate base. So pushing it to the left, the equilibrium position will lie over there on the reactants side. Cn is also, once again, declaring the stronger conjugate base. That pushes the equilibrium position to the left for the reactants, giving us K being less than 1. Now for the fun calculation part, finding the value for K. How would you go about something like this? Well, we have two different acids reacting and basically are all aqueous, so they're in water. So we would write them out as their separate equilibrium positions in water. So we have HCN plus water giving us, because this is the Ka for it in pure water, H2O. So we get the cyanide plus the hydronium, right? Because this H is going to be the one given away. And this is, the Ka is 6.2 times 10 to the minus 10. For the other reaction, we have hydrofluoric acid in water, like so, and we would get fluoride and hydronium out of that. And this is where we get this Ka value, because the Ka, of course, is measured at 25 degrees. Celsius in pure water. So this Ka is 7.2 times 10 to the minus 4. Setting up those first, where we have them in their natural settings as they, this is the equilibrium positions they would form in water. That's what their Ka values tell us. So now what you need to realize is we're just going to apply regular equilibrium concepts here, where we want to arrange it so hydrocyanic is the reactant 1, fluoride is the reactant number 2. This would be product 1, and this would be product number 2 here. So if I'm looking at that, I need to flip this one, change it over, flip it the other direction. So this is going to be, the H3O plus F minus going this direction is going to give us the water and the hydrofluoric, like so. That also makes my Ka turn into 1 over 7.2 times 10 to the minus 4, because remember, when you flip any kind of equilibrium constant, it becomes the reciprocal of that. So this makes us be able to cancel. So we cancel the hydroniums out. We do cancel out the waters, and we end up with our hydrocyanic, our fluoride. We get our cyanide in here, and our hydrofluoric. So hydrocyanic plus fluoride gives us cyanide plus hydrofluoric, which does fit this overall reaction at the top. So this is just using that way of being able to manipulate equilibrium constants. So really we need this one and this one. So it ends up being 6.2 times 10 to the minus 10 times the 1 over 7.2 times 10 to the minus 4. When you calculate that, basically it's just a division problem. 6.2 times 10 to the minus 10 divided by 7.2 10 to the minus 4. We get our new equilibrium constant, which happens to be 8.6 times 10 to the minus 7, like so. And that would be the equilibrium constant if you mixed these two different acids together, like so. All right, now we're going to start looking at how to do the equilibrium positions for weak acids. Calculate the pH of a 0.5 molar aqueous solution of the weak acid HF. We have the Ka value here. What are the possibilities for the dominant reaction? We have our HF. Of course, we have our water, and which one would control the pH? Well, we saw that the Ka value for the hydrofluoric and the concentration being 0.5, it's going to be much higher. So the top one, this is going to control it. And we look at, like I said, looking at their Kas here, 10 to the minus 4. This is going to be a much stronger one out of the two. So definitely the HF reaction is the one that's controlling the pH. FHF, because the Ka is definitely larger. Set up a rice table for this one. So you put your reaction at the top. HF plus water gives you the hydronium and the fluoride. Now, we're going to put in the initial concentration. Don't forget that water is a liquid, so we basically cross that one out. Now, following regular deals, since we know we're just doing regular equilibrium in pure water, how much is going to ionize. These guys start out at 0, so that means that we know it's going to go to the right to get to equilibrium. So this is going to be minus x. This would be plus x. This would be plus x. So at equilibrium, you get 0.50 minus x, plus x, and plus x. And before we can do anything else, we need to go ahead and write out our expression for Ka. So Ka equals concentration of the hydronium, which is the first product, times the concentration, let me fix that, times the concentration of the fluoride, which is the second product, all over the concentration of the HF, which is the only reactant we will include because water does not count. So here we have that all nicely set up. Now all you have to do is plug in the numbers. And this is what we do, is we plug in our 7.2 times 10 to the minus 4. Now it's going to be x times x on the top. And this right here ends up being x squared over 0.5 minus x. Now, like before in KSP, what we were able to do here is eliminate the x. You are allowed to do this in acids and bases as well. However, you need to be a little bit careful. You have to really evaluate your Ka over here and make sure that the x is going to be less than 5%. 5% of the overall terms of ionizing. It's called the 5% rule. If you know that it's going to be less than 5%, you are allowed to eliminate it. And the way you can pretty much tell, usually anything that's 10 to the minus 4 and smaller is going to fit the 5% rule. 10 to the minus 3s, I always have to double check. Anything larger than that, like 10 to the minus 2, of course, definitely wouldn't eliminate. And if you can't eliminate x, you know, because you would say eliminate x, let me spell correctly, you know, too small, it's negligible, too small to affect the 0.5 number. You are allowed to do it if it falls within that 5%. Okay, and I'll show you how to check that in just a second. But if it doesn't fall within that 5%, then you would just graph it. You would use, do the graphing. Graph it, you can always do that instead of the quadratic, to check the x and make sure that, or you could do the 5% rule and check that as well. So we will check the 5% here and make sure that that works. All you have to do is once you find your x where you solved it without, you just did the 7.2 times 10 to the minus 4 equals x squared over 0.5 where you took the x out. This is the value that you get for x. Now all you have to do to check it is do 0.019 over 0.5 times 100, like so. And if that ends up being less than 5%, then it's good to eliminate x. And it does, because if I do that and multiply it by 100, this is approximately 3.8%, which is definitely less than that 5%. So I'm allowed to eliminate x here. Once you get the x concentration, what you should notice, the x concentration is also the concentration of the hydronium. So we can do the negative log of the hydronium here, like so, the negative log of the hydronium, and we will take that value and that ends up giving us our 1.72 for our pH. All right, so if it's less than 5% of the original acid, it can be ignored or removed from the calculation. This is called the 5% rule. Ka values less than 1 times 10 to the minus 4 usually allow for the 5% rule. When in doubt, check it. All you have to do is do that concentration of the hydronium at equilibrium divided by the original HA concentration, the initial one, times 100. And then you can check the percent and make sure that it's, has to be less than 5% in order to eliminate that X. All right, and this also is the same formula for just looking at percent ionization. The H plus, or you could say the hydronium, at equilibrium divided by the initial acid times 100 is going to give you the amount ionized. And like I said, 5% or less is ionized, you're allowed to eliminate that X value. But you will also be looking for and calculating percent ionization for certain problems.